we are going to sketch a graph of this rational function. The first step is to factor the numerator and the denominator. Well, the numerator is already factored fully, but the denominator can be factored. So take a minute, factor the denominator. All right, so here's what you should have gotten. Okay, so now what we're going to do is we're going to look for common factors between the numerator and denominator. Well, these may not look identical, but they really are very nicely related. Whenever you see something like x minus 2 and then you see 2 minus x, well, we know that these are related as negatives of one another. So these actually are related nicely. What we can do, in other words, is we can write the numerator as negative x minus 2. And now we see that, yes, there is a common factor between the numerator and denominator, so I can cross these out. What am I left with? Well, I'm left with negative 1 over x minus 2. Now, one thing we should always consider is whenever we cancel common factors is whether we change the domain of definition of our function. In other words, is this function defined for different values of x than this function is? Well, in this particular case, the answer is no. They have the same domain of definition. The only place this function is undefined is at x equals 2, and the same is true of this function. So we do not need to stipulate anything special. Now let's think about what aspects of the graph we can discern by looking at this expression. Well, one thing I can look for are x-intercepts. X-intercepts are the values of x that are going to make the numerator equal to 0. Well, here the numerator doesn't depend on x. It's always equal to negative 1. It's never equal to 0, so there are no x-intercepts. Second thing I can look for are asymptotes. Does this have any asymptotes? Well, I can find vertical asymptotes where the denominator is equal to 0. And yes, that does happen. Notice that the denominator is equal to 0 when x equals 2. So x equals 2 will be a vertical asymptote. Next, we can look for horizontal asymptotes. For horizontal asymptotes, we look for the highest order terms in the numerator and denominator. The only term in the numerator is negative 1, so that is the highest term. The highest order term in the denominator is x. So for the horizontal asymptotes, we're looking at negative 1 over x. Now, what I need to consider here is what does this expression approach when x gets large? Well, when x becomes a very large value, this quantity will become close to 0 because I'll be dividing 1 by, or negative 1 in this case, by a very large number. That gives me 0. So if ever you have a higher order term in the denominator left over than you do in the numerator, when you block off the lower order terms, then 0 is going to be the horizontal asymptote. So we have a horizontal asymptote of 0. So let's go ahead and plot this expression. We noted that there is a vertical asymptote at x equals 2. And there's a horizontal asymptote of 0. So it's going to be approaching this x-axis, the line through y equals 0. Now there's not a lot of information here left to graph this function. So what we're going to have to do is find some other points on the graph. One other point we can try to find is the y-intercept. Now you could pick any point here, but I like the y-intercept because that involves plugging in 0 for x. If I plug in 0 for x, I am left with negative 1 over negative 2. I'm left with 1/2. So if we mark values on the y-axis like this, we know it's going to cross the y-axis there. Now, because it has this as a vertical asymptote and this is a horizontal asymptote down here, we know that the graph must look something like this. Now, what does it do to the right of this vertical asymptote? The graph could live up here, or it could live down here. Which is it? Well, let's plug in a number over there and see. Let's plug in 3 for x. If I plug in 3 for x, what I get is negative 1 divided by 1. I get negative 1 as an answer. So I know that at 3, the height of the graph is negative 1. And so we see that we must be down here. And again, obeying the asymptotes, I know that the graph has to have this behavior. And that completes a sketch of this graph.